Hi everyone. So we were talking about zeros and poles, section 19.4. Okay, so let's start with zeros. Um, Here we will study um, functions that have Lorentz series. So, k is in integers, ak, and then z minus z naught to the k. So we will have principal and um, analytic part. So these are the function we're studying. We are not looking, you know, at things like log z that that don't have um, Lorentz series. Okay, definition. A function f has a zero at z naught of order n uh, if you have f of the nth derivative of f, it's not zero, but f of 1 and f of n minus 1, they are all 0. Okay, so this guy is the smallest integer that is non-zero, and all the other guys up to it are 0. Equivalently, um, f of z over z minus z naught to the n is not 0, and um, at z naught, and it's analytic. Okay, so um, right, we pick the smallest such n. And by smallest, we mean this guy is not 0, but all the other guys are 0. Okay, so let's do some examples here. Let's start very easy. F of z equal to z to the minus I over 3. Well, it has a pole at a 0 at z not equal to I. And what is the order? Well, you can say it's 3, but let's do it a bit formally. We have f of z over z minus I to the 3. Well, this is just 1, right? Which is not 0. And okay, but let's see. Is this the smallest such n? Um, so okay, so let's see. If I divide by z minus I to the 2, well, I get z minus I, right? Uh, which is equal to 0 at z equal to I. Okay, so this guy is the smallest one, if you like. Uh, yeah, okay. Let's do another example. Um, yeah, f of z is equal to z to the 4 minus 16. Okay, so well, here first you have to find the roots. First find the roots, and we have that f of z can be written as z minus 2, z plus 2, z minus 2i, and z plus 2i. So it has um, four roots, and what is their order? Well, again, we want to find, let's just look at one of them since they have the same exponent. Let's say 2. Well, we have f of z over z minus 2 to the n. What is that? Well, we have z minus z naught to the n minus 1, sorry, 2, and then the other guys. Okay. All right. Now, um, at z not equal to 2, um, this function is not 0, so that's fine. That's condition 1. But it's only analytic only for n equal to 1. Otherwise, you get a pole here. Okay, so the order um, is n equal to 1. Okay, um, now that I gave you a bit of intuition, let me come back and explain this step. So what is going on here? Call it star. So all we're saying there, so um, argument for star is from a Taylor expansion, right? So we have f of z, z minus z naught to the n, and um, write down all the terms. So okay, um, so now we want this guy to be analytic, and we have so let me write ak k minus n. Well, this guy, first of all, we want this to be positive, so we want k to be bigger than n, right? Otherwise, so we don't want to have things of this form, right? So we have that k must be greater or equal than n, okay, in order for this ratio to be analytic, okay, and that implies that a1, so a0, a1 to an minus 1 have to be equal to 0. Okay, let's see how we're doing with time. All right. Okay, good. Okay, one more example for 0. F of z is equal to the z squared minus 1, and we're looking at z naught equals 0. Well, as usual, expand. So let's expand the exponential around z equals 0. So we have z squared and 2 factorial z to the 4. So 1 plus. So that's the exponential minus 1. The 1's cancel out. And let's factor out z squared. You will see why. Okay, so now coming back to our question, um, we have f of z divided by z to the n. So this is z squared minus 1, and it's z squared 1 plus z to the n. So once again, what do we have? We have z to the n minus 2 and all that stuff. And this guy is not 0 at z equals 0, right? If you plug in 0, this guy becomes 1. And it's analytic only for n equal to 2. So it's not 0 is equal 0, and you require, so let me say that as well. Um, you need n, you don't want n to be on the top. So let me write it this way. So you don't want to have this happening. You don't want 2 to be bigger than n. Okay, so and when, so you want the opposite. You want n to be less or equal than 2. But you also want it to be analytic. So only for n bigger than equal than 2. So these two together force n to be 2. Okay, so that's the idea. That's one way to find the order. Let me do it another way. So that's one way. Another way is, and you pick the one you like. Uh, we just have easy square minus 1, and you know you want to expand this, right? So we have, so this is f, and the question is find its Taylor expansion. Okay, and we already wrote it above. It was z squared, z to the 4, and so on. And yeah, this is a bit easier to see. So again, uh, this is the Taylor expansion. And we have that f of the second term here, the second derivative at 0, is not 0, right? So we have f of 1 is 0 because there is no z term. Okay, so yeah, this is a bit easier, much easier. So therefore the order is n equal to 2. Okay, so that's it for zeros. Next